our webinar. Thank you for joining us. Today's webinar is on accelerating more sustainable battery design processes from molecules to neighborhoods. I'm Allie McPherson. I direct the Investor Environmental Health Network for Clean Production Action. CPA is a nonprofit dedicated to advancing strategic solutions for safer chemicals and products. And we partner with the University of Buffalo on CORE, which is the Collaboratory for the Regenerative Economy. And we have focused for the last 7 years on how to accelerate the transition to safer chemistries and renewable energy systems. This webinar is a part of a broader series of webinars we've hosted, co-hosted, focused on community right to know, environmental health data, data equity, and tools and market drivers needed to accelerate the transition to safer chemistries. And we're really proud to co-host this series with GAIA, whose leadership in addressing community impacts from battery production, use, and end-of-life management has really been foundational to our solutions-oriented work. So just quickly, why batteries? So as we make this global transition to cleaner energy systems, and we face this huge defining question, how do we build a battery-powered future that is not only low carbon, but committed to safer, more responsible, and equitable material and chemicals across the battery sector's value chain? And this is the conversation that we're going to really center on today, this challenge and then the solutions needed to address it. And we know that batteries are essential to scaling renewable energy technologies, but we also know that they're really very dependent on toxic chemistries that affect workers, communities, and ecosystems. So the 3 key outcomes that we're hoping to advance today, one is just a clearer understanding of the urgency and transition to safer chemistries in batteries. 2, insight into new tools and data-driven pathways to identify safer substitutes to chemicals and materials like PFAS and other hazardous materials. And then 3, hopefully encouraging you to join our network. Your participation and leadership is really essential in driving this transition forward. We have 3 fantastic speakers today. Helen Holder will start us off. She's formerly with Aniobel and HP. She really is a technical and strategic leader in looking at battery chemistries and opportunities for safer material innovation. Chris Helt is the director of Green Screen at Clean Production Action. He will share how hazard assessment tools help industry identify safer alternatives and avoid regrettable substitutes. And then finally, Dr. Krishna Rajan with the University of Buffalo will show how AI, informatics, and material science are really transforming the way we think about material design and development. We'll begin with 15-minute presentations from each speaker, followed by a Q&A and panel discussion. I encourage you to put comments and questions in the chat at any time. With that, I'd like to introduce Helen Holder, who's been a longtime collaborator and leader with Clean Production Action, a pioneer in sustainable tech at HP, and most recently part of a battery startup at Aniobel, and now head of strategy for Tetra Mem. Helen, the floor is yours.
Great. Thank you so much for having me. And it's so nice to be with friends that I've known for a long time. So one of the things that I was asked to do was share a little bit of perspective on compare and contrast some of the earlier work that we did for with chemical hazard assessment, with complying with the ROS restrictions versus kind of what's happening in the battery space now, because the green screen tool, that's kind of how I got connected to Clean Production Action and BizNGO was for the ROS restrictions. And so I'm going to give you a little bit of that history and the role that chemical hazard assessment played in that work. And then I'm going to actually then pivot over to what I learned developing sustainable battery materials. So let me go ahead and start. Next slide. So this is actually the most dangerous slide that I have because I could literally talk about this all day. So I'm going to try to keep this brief. And if anyone has any questions about this afterwards, please feel free to get in touch. We also published, at the bottom, you can see some references we joint published with Clean Production Action and EPA about a lot of the work that we did in this space. So let's talk a little bit about raw. So the whole reason that I got into sustainability really was because of these restrictions out of the EU. Because before those restrictions were coming into force, I was an engineer qualifying materials, solders and other materials in electronic products. And when the ROS restrictions were impending, HP and other electronics companies needed people to qualify the replacement parts, or the parts that had phased out those materials. And that's kind of how I got pressed into service into this field. So I don't have a sustainability degree, or I'm sure many of you do have that background, but I don't. I was doing component reliability and manufacturability. And so what the ROS restrictions did was there was a list of specific substances and classes of substances. So lead and lead compounds, cadmium, cadmium compounds, hexavalent chromium, mercury compounds, and some brominated flame retardants. And that was it was kind of crazy kind of looking back on it. So it was every component in every piece of electronics. And so those substances might have uh, any number of functions within those components. And so we had thousands of components, hundreds of compounds, and we had to get this all done by July 1st, 2006. And so we needed to be able to qualify these parts pretty quickly. Now, the question that I asked was, if we're getting rid of these substances because of a sustainability problem, the e-waste problem, we should make sure that what we replace it with is actually better than what we're getting rid of, which sounds really obvious when I say it, but it really wasn't obvious back then. And so we started looking for how do you know whether something is going to give you a regrettable substitution? And that's how got connected to the green screen and chemical hazard assessment. And these were very early days in some of this, but the point here is that that tool was very helpful because we could quickly screen out regrettable substitutions. And it was very important to be able to do that because I didn't want to have to go back and requalify all these parts. So I didn't want to put one phthalate in and then 2 years later have another phthalate get restricted. I wanted to be able to look at all of the replacements and make sure that it was not going to be a future restriction. And chemical hazard assessment was really good for that because it's a little bit narrower than some of the more holistic tools, and really got to the heart of what Ross was about, which was dealing with this toxicity specifically at end of life of electronics, which was a known problem. Now, in the battery space, this is slightly different because it's a little narrower because it's only batteries. And I'm lumping kind of all of the battery regulations into one bucket here. There are differences, but in general, it's limited to batteries. And the substances are often restricted through other regulations like REACH. And one thing that's really different is that the chemicals that are of interest in batteries actually do have similar functions within electrochemical cells or within whatever process that they're associated with. And that is slightly different than ROS, where we had to cover lots of different functions and lots of different components. This is a little narrower. And that's not to say there's not a big world of chemistry in battery. There is, but relatively speaking, it's a little bit narrower. Now, what I think is really the most important difference, though, between them was that Ross was dealing with an existing problem that was recognized. E-waste was widely recognized as being a problem. There were these photos from China of just mountains of e-waste, and we had actually a relatively good sense of that this was a real problem. I think that in the battery space, one of the things that's is good is we're trying to get ahead of what may happen in this space. But it also means that we need to be fairly conservative and precautionary because some of those impacts are not fully understood yet. And so the standard for what we would do a substitution in is quite high. We want to make sure that we're really sure we're going in the right direction. And again, chemical hazard in this is actually also very helpful because you can have that grade between benchmarks, for example, where you really have a better sense that you're going in the right direction. So slightly different use of the tool, but still really useful in both cases. Next slide, please. So batteries are chemistry. Literally, that is literally what they do. And this is slightly different again from electronics components, other components. Batteries are not only functionally in their service life actively having reactions. That is literally what it does, is storing energy chemically and then releasing it. But in every single phase of the value chain in the life cycle, every single step is very chemically intensive. And again, that means that a chemical focus tool is a very appropriate tool for looking at each of these steps. Now, I will call out at the bottom here, Volta Foundation. So this graphic comes from the Volta Foundation Battery Report for 2024. Anyone who's working in the battery space really should be reading these reports. They come out annually. They have a lot of great information, what's going on in the industry. It goes into the different chemistries, kind of where they are, state of the art. And I just highly recommend you be knowledgeable about the industry that you're trying to influence. And this is a great way to get an accelerated understanding of what's going on in that industry. Next slide, please. All right, this is really kind of the main idea here. Hazard assessment is complementary to LCA. So life cycle assessment is very commonly being used in batteries and in many, many ways, but in particular in battery space. Not uncommon for that to be global warming potential to be a required KPI to be reported. And that's fine. That's great. It doesn't, but LCA doesn't do that deep granular view of what a chemistry does or a replacement chemical, what it might look like. A lot of related chemicals are actually going to look very similar in an LCA, but if you look at them in with a green screen or another chemical hazard assessment tool, you're going to see really big differences between them. And so, and what you don't want to do is you don't want to spend a huge amount of resources doing a life cycle assessment, life cycle analysis for for chemicals that are both equally chemical hazardous. And so, by screening out some of those um, already known problematic chemicals, you'll save yourself a ton of time. You don't want to spend that time on your LCA. So I think these are very complementary tools. And again, I have some references down here that are worth checking out. In particular, some of the meta reviews of LCAs. The Porzio article I find to be a very good it's very good at capturing all of the different stages of the life cycle from a technical perspective. I thought that it was probably one of the better ones that just nailed all of those different steps. So I would just recommend you check those out. Okay, that's all I'm going to say on chemical hazard assessment because the other speakers are going to have a lot more to say about this. Mostly want to just share with you that this has been a very valuable tool, and I think that it really helped us have a greater confidence that the substitutions that we were making were not going to be regrettable substitutions. All right, next slide. All right, so what did I learn in the battery startup, Ionabel, as we were developing sustainable battery materials? Next slide. Um, Number one, China dominates. And this is the reality that you just can't get away from. So any initiative that you're going to do in the battery space that's trying to be more sustainable or anything, but more sustainable, either has to include or at least account for the fact that China is the center of the battery world. If you're not talking to CATL, if you're not talking to BYD, if you're not talking to Goshen, you're really kind of not really moving the needle. So that's just something you have to, this is just like gravity. It's what it is. You can see in this graphic here that even in places where China isn't leading the extraction of certain substances, they're often leading the refining of that substance. And although there is more cell manufacturing outside of China now than there was just, a couple years ago, it's still heavily dominated by China. So this is just the reality that, again, if you want to be in this game, you have to be working with China. Next slide. Cost drives everything. So the way the China industrial policy works is that when they have an area of interest, they put a lot of money into it. And what that usually ends up is overbuilding capacity by a significant amount. We saw this in printed circuit boards 25 years ago, but now you see it in battery. And so there's a huge amount of overcapacity, 20, 30, 40% overcapacity in China. And that forces a huge amount of competition and all of the costs come down. It matures and solidifies the processes that they are using. And what that means is that they are very cost sensitive to new material costs, and they're very resistant to changing the manufacturing process. And I'll give you a specific example of that in the next slide. But basically, this is if you are doing sustainable material development for the battery space, and that material is not cheaper than what they're already using, it is not going to be a good conversation. That's not going to go well. And just because they're holding on for, for dear life because there's so much overcapacity and so much cost pressure. Next slide. Oh, formatting on this one got weird. Okay, there is no drop in. So if you look at this graphic, this is also from the Volta Foundation. I would encourage anyone who is working in this space to become very familiar with all of these processes. And there's actually a link that you can't see because it's off the bottom of the screen of a CATL, a tour of a CATL factory. I encourage you to watch that and just kind of learn as much about it because batteries are very complicated. And even small changes require a lot of testing and optimization. And I'll give you our specific case. So Ionabel makes a silicon nanoparticle for the anode, and that is to displace graphite. Today, most anodes are graphite, and they use a binder, which is a blend of CMC and SBR. That is not an appropriate binder for a silicon anode. And if you wanted to test our material, you really can't use that CMC SBR as your binder. You have to use a polyamide imide or a polyimide as your binder. And this is actually fairly accepted from a science perspective. But when we dealt with the big battery companies for their R&D departments, they insisted on always testing our silicon material with the CMC SBR that they use in their manufacturing, which generally means that the material doesn't meet the expectations. They can't reproduce our results because they're using an incorrect formulation. But because they're under a huge amount of pressure to not change anything in their own process, this is what they're doing as new materials are coming in. They're not being tested appropriately. So this is just to give you a sense, again, if you're doing a new material, it may not get a fair hearing, I don't know what you'd call it, a fair test, because of the way that there's so much pressure to use their existing processes and materials. All right, next slide. This was a huge surprise for me. So KPIs are traded for cost. So back when LFP was being looked at as a cathode material, we kind of dismissed it because it's lower capacity. And we said there's no way that people are going to use that because people with EVs have range anxiety. We want more capacity, more energy density. And that is not how this is played out at all. LFP has been widely embraced, even though it has lower capacity than NMC because it's lower cost. And so this is good news, I think, if you had a sustainable material, as long as it costs less, there may be some room to do some trade-offs in there. The one thing you can't really trade off too much is cycle life. Cycle life is still kind of king, but everything else seems to be negotiable. Next slide. So this was the most surprising and frustrating thing that we learned. EHS is super hard for startups in this space. Even if you've got a sustainable material and a sustainable process, you can't make it in your kitchen. You still actually have to scale this up, and you need to get industrial hygiene expertise and EH&S expertise, and getting that support as a startup was super, super hard. And I even have network of people like the hosts of this event, and reaching out through my own connections, I still couldn't really get all the help that I needed. Thankfully, I had enough knowledge to be able to do it myself and where I needed it. But the consultancies were incredibly expensive if you could even get them to be interested in these kind of a small project to them. And then if you wanted to hire, there's just not a huge pool of people that you can pull into a startup environment that can do this. So this was really probably one of the biggest surprises, is that we just couldn't get the help that we needed for that scale up industrial hygiene and EH&S. So that is, I'm going to stop now because I know this is quite a lot, quite a lot of content. We've got some other speakers who have some good things to share with us today. So we'll take, I think, one question. Is that, I think that was our plan, was to take one question.
Yes, and I don't know if I can totally see the chat. And if there are no questions, we're gonna have time for a broader Q&A at the end, but we were gonna give everyone like a breather in between. Are there any questions in the chat that Mike or anyone else can see?
There's a question to define acronyms.
Oh, I use a ton of them. So tell you what, when we open it up for general questions at the end, if there's a specific one that I have not defined, then I'm happy to do that. Or if there's a specific one, you can put it in chat and I'll answer.
That'd be good. We could do some of that translational work and follow up to the webinar too. I appreciate the acronym issue. All right, well, just in the interest of time, I would like to just thank Helen. I mean, that was an incredible overview. And I think it also was really insightful to see the lessons learned. So I'm excited to come back to that in the panel discussion and have your sort of leadership in this space. So next, I'd like to welcome my colleague, Chris Helt. He is the director of the Green Screen for Safer Chemicals, which is housed at Clean Production Action. Chris is going to discuss how the green screen is being used globally across electronics, packaging, and other sectors to identify inherently safer alternatives and support market transformation. So I'll hand it over to you, Chris.
Thank you, Ali. And hello, everyone. Welcome to the call. And yep, we can go on to the title slide. There we go. So the goal that I have today is really to give you an introduction to the Green Screen program here at CPA. And I'm going to break it down into the different phases that organizations are likely to use as they take steps towards identifying hazardous chemicals and then working towards safer solutions for those chemicals. You can go ahead and hit the next slide. And so yeah, just grounding us quickly on the mission and function of Clean Production Action as it relates to the Green Screen program specifically. Ali had mentioned initially that, our mission is to design and deliver strategic solutions for green chemicals, and this drives sustainable materials and environmentally preferable products. And really, that's the distillation of the tools that I'm going to talk about today, right? So we have, what we've done with the Green Screen program and the Green Screen tools is really deliver a system that works for organizations such as manufacturers, brands, other nonprofits who want to reference hazardous chemicals and how to build and work towards safer alternatives. And those tools are available in the market, and they're currently being used to create safer materials, safer products. So as we go to the next slide, you can get a sense of the organizations that are using our systems. Next slide, please. And the users of our work and tools range from state and local governments to the United States federal government with their federal purchasing program, along with industry leaders such as Apple and HP, Samsung, and then organizations like retailers who are interested in knowing the products that they sell on their shelf. Do they have hazardous chemicals? Do they not? And so what we have here is really a network of organizations who are interested in identifying hazardous chemicals and working towards safer alternatives using the criteria and metrics that we have with Green Screen. Next slide, please. So I mentioned the path to safer products and safer materials. So this slide really encapsulates the three primary tools I'm going to be talking about today. And if we start at the left-hand side, you see that we have what's called the Green Screen List Translator, which is a quick screening tool to identify chemicals of concern. And this is usually the first step for organizations, especially manufacturers and companies that want to avoid hazardous chemicals, right? So they want to screen against what is known to be a hazardous substance, a hazardous chemical. So the Green Screen List Translator is a tool for those cases, for those organizations. From there, where does a company go, right? So if you know what is bad and you've eliminated that from your product or your supply chain, that's very good. But you don't actually know if there's a better alternative for specific chemistries where there has been a hazard identified. And that's where the Green Screen for Safer Chemicals criteria comes in. So that's the top portion there, the top of the triangle. And in that case, instead of just avoiding what is bad, you can identify safer alternatives that are less hazardous, inherently safer because they don't present a lot of the toxic issues that hazardous chemicals have. From there, instead of just working at the chemical level, it's important to work at the material and product level. So we have at Green Screen a product certification system, which verifies compliance against the other two tools at the entire product level, right? So companies and especially consumers are purchasing products or materials. They want to know that that material itself is meeting a certain threshold of safety. And that's where we've taken the other tools and built them into a product level system where we can verify compliance with hazard avoidance and the safety criteria from Green Screen for Safer Chemicals. So let's step through these tools pretty quickly, but I do want to give you a sense of how these systems work. Next slide, please. So starting out with the Green Screen List Translator. So this is really designed to be a high throughput, quick level of assessment for companies that want to identify the chemicals that are in their product and determine the chemicals that are in their product or their supply chain or the products that are on their shelf, the chemistries that are being sold by retailers, et cetera. It's designed to work for companies to identify listed hazardous substances in those products or materials. So what we've done here is we've taken what we call Green Screen criteria, where we reference authoritative and scientific lists where chemistries have already been cited to be a carcinogen, a mutagen, a reproductive toxicant, or other type of hazardous, have other types of hazardous properties. And we have built a list of lists so that you can use a Green Screen List Translator approach to determine if that chemical has already been cited, is it an issue, should you eliminate it from your product or supply chain. So this is a fast approach because it is all automated using the lists that are already out there. And we've worked with platform providers with this criteria so that companies can put hundreds of chemicals into the system, screen them quickly and determine, okay, yes, we have a problem with these chemistries and we should remove them from our products and we should define safer solutions. Next slide, please. This is just a graphic of what that process looks like, right? So you could start with thousands of chemicals. A company could use a screening system that's provided by one of our automated service providers. They use the criteria of the Green Screen List Translator, and that helps them identify and prioritize. They have X number of chemicals that are hazardous. We define those as List Translator 1, so LT1 chemicals in our system. There are other criteria for if something is not listed, but the worst of the worst is defined as an LT1 chemical. So again, it's really powerful as a starting point to say, okay, we know what chemicals are in our product or our supply chain. Let's take a look and see if there are issues with those chemistries. Next slide, please. This is just an example of what that looks like in the real world. So here's a chemical that has been put through the Green Screen system. And if you click the button, we'll have the animation to see the highlight here. But what we have is a list translator score. At the bottom there, you see that there is an LT1 value associated with this chemical. And that was defined based on where you see the red or pink circles there to the right. So what's happened in a completely automated fashion is that our system and criteria have been applied to this chemical. It has been determined to be a carcinogen, a reproductive toxicant, developmental issues. That's all been done using the list-based approach. And using the criteria that we have in place, it's defined this as a problematic chemical, which is a list translator 1. So it's likely what we call a benchmark 1 chemical, which is the worst of the worst when it comes to hazardous substances. You also see there above that, there's a benchmark 1 listing, and I'll talk about that here in a moment. That is the in-depth, thorough, granular approach that Helen mentioned, that you can have a really fine-tuned attention put on some of these endpoints. Next slide, please. This is just letting you know that we have 2 service providers that provide this platform that screen against the list translator criteria, 3E Exchange and the Pharos system from Habitable Future. So the system is accessible, is currently being used by plenty of companies, many companies, to help them prioritize the chemistries in their products or supply chains. Next slide. Now, and you can click the button for the animation. So so what do you do when you have a chemical that is novel, that has not been listed, and you're working with a material that uses that novel chemistry, and you want to know if it has hazardous properties? So it's not, it hasn't been used in the market enough. It's not been listed as a carcinogen. It's not been put in the list translator system. You have to use a forward-thinking approach where you apply specific toxicology principles to understand, is the chemical hazardous, and what does that, what are the toxicity properties of that chemical? This is where Green Screen for Safer Chemicals comes in. It is a fully transparent, scientifically based method to take a very granular look at those novel chemistries with each of a number of hazard endpoints to determine if there's an issue or if there is not. So again, this goes beyond the list-based kind of regulatory-based approach, and it's really proactive to understand where is there a toxicity issue, and if there's not, is the chemical safer? Could it be used as a safer alternative instead of a hazardous material? This is used by many different organizations, tox firms, companies, NGOs. Green screen assessments are performed by profilers that we have trained. So we have toxicologists who we have worked with. We have brought them up to speed on these criteria. They perform green screen assessments, and they assign what are called benchmark scores to the chemicals that they work with. Let's click the button, and we'll go to the next slide here and take a look at the benchmark scores. So, again, getting back to the pathway for improvement. Companies will eliminate what is bad, and then they have to work towards what is good. So here's the kind of stair-step approach to get to the good types of chemistries that are less hazardous. Benchmark 1 is seen as the worst of the worst chemicals that are out there. This is similar to the list translator. So we know those listed chemicals are the worst of the worst. But the benchmark 1 is a similar approach where it's a granular examination of a chemical. And we have determined that they should be avoided and not used in products. Working up from there, we have benchmark 2. It's less hazardous than benchmark 1, but there's still an opportunity for a safer substitute. Again, going to benchmark 3, even less hazardous. And then benchmark 4, this is a preferred safer chemical. So this gives a North Star to understand what the goal is, right? So we want less hazardous preferred chemistries using green screen criteria, using the assessment methodology that we have in place. Next slide, please. This is just letting you know that we have very fine-tuned criteria for each of the benchmark levels using toxicology principles. So here you see the common terms, carcinogens, persistence, bioaccumulation. Moving up the ladder, we have things like eye irritation and skin sensitization. Those are, less, relatively less hazardous types of endpoints. And we have specific criteria for each of the tiers to define what is less hazardous and therefore inherently safer than the tier below. So this is a toxicologist's dream, and this is a good thing that we have specific criteria. Next button, please, or next slide. Again, this is a toxicology lens of the criteria. There's nothing surprising here based on the traditional tox-based approach. We have the main important endpoints of CMRs. We have PBTs on the list for persistence, bioaccumulation, and toxicity that are relevant for environmental toxicity and fate. What's important here, I want to highlight, is that we have groupings, right? So we have human health group 1, human health group 2, environmental toxicity, physical hazards. That helps us define the specific criteria for benchmark 1, 2, 3, 4. Just as I mentioned, I think we would agree that cancer is a relatively more important endpoint than eye irritation, and the system acknowledges those types of nuances in the benchmark determination. Next slide, please. This is what those endpoints look like in a green screen assessment. And in this case, you see just a generic chemical. And the important factor here is that red is bad, green is good, and that profilers assign hazard classifications for each of the 18 endpoints on this screen for a chemical that they're performing the assessment for. So this will define at the individual endpoint level where there are issues with the chemical, and they are going to roll up into that benchmark score of 1, 2, 3, 4 that we talked about. Next slide, please. This is an example of methylene chloride, and Helen had this in her slide presentation as well. Just want to walk through very quickly an example of the system as used to identify safer alternatives. If you click the button, you see here that methylene chloride has inherent hazards for cancer. It has an issue with neurotoxicity, and there's other endpoints here that are lighting up very dark red or red, which indicates that it's likely benchmark 1 and it's hazardous. There are a lot of issues with methylene chloride. There are a lot of alternative solvents. So on the left-hand side, we have benzyl alcohol down to caustic soda. These are all chemicals in the same category of solvents that could be used in electronics manufacturing or process chemistry. And what we could do is, if we click the slide button, we can see what those endpoints look like in our system of green screen. Now, if this looks very confusing and overwhelming, that's understandable. I'm overwhelmed by all this as well, but we can click the button. And what we're going to do is take that lens of the benchmark scores. If you click the slide, we're going to take that and apply that to these chemistries. If you click twice now, the slide for the animation, we can take a look at what the benchmark scores look like. Go ahead and click. And again. So here is what the benchmark looks like, right? So we've taken all of that complex endpoint data, distilled it down into these 1, 2, 3, 4 acknowledgements for the benchmark. So at the bottom, we have methylene chloride, methanol, and toluene. Those are the worst according to our hazard-based criteria. It's a little bit less hazardous, but still used, but search for safer substitutes are benchmark 2, and they range from benzyl alcohol down to caustic soda. There is one chemical, is benchmark 3, so this would be something that we would acknowledge as a safer alternative, right? So it's an alternative that has been identified as benchmark 3. It's still used, but there is a little bit of opportunity to go to benchmark 4. So this is a direct application of the green screen criteria in our system that has been applied in the market. Next slide, please. And I will go very quickly because I think I could be getting over time here in a moment. But as I mentioned, the main point in the consumer product space is products themselves and materials. So consumers purchase materials, retailers purchase products and materials. And what we've done to acknowledge that is we've built a product level certification that has the foundation of the Green Screen List Translator and Green Screen for Safer Chemicals criteria. And it is used at the product level to define safer products based on the hazard-based criteria that we have at the lower levels for the chemistries that are used in those products. Go ahead and click the button. And this tool of Green Screen Certified is really very powerful to have a conversation or to aid in the conversation between purchasers and users and suppliers and manufacturers and supply chains, right? So once a product meets the specified criteria that we have for a product category, there's an understanding that, okay, it does not contain any specific list translator chemicals. It doesn't have any benchmark 1 or potentially benchmark 2 chemistries, because we have different tiers of certification for the products. And it's a very clear statement that is relevant as part of third-party verification, right? So we have, again, profilers and reviewers who are third-party to the manufacturers, who perform verification against our requirements, and they ensure that all the requirements have been met and the product can actually receive the certification. So we issue a certification based on that third-party verification. So this is extremely helpful in the conversation to help level the playing field to understand, okay, a product has met a certain threshold, it does not contain certain hazardous chemistries, and it does use safer alternatives. Next slide. This is just a few more bullet points about the Green Screen Certified program. It's a globally trusted eco-label. To date, we have over 250, and I think it's actually 270, the slide is a little bit old, of products that have gone through the system from over 30 manufacturers. And this is, again, used by many companies to define and understand what is safer for their work. We issue certificates and we list products on our website based on the verification. Next slide, please. This is just a summary of the types of products that we certify, which include cleaners and degreasers in manufacturing. This standard was actually built for the electronics industry to help companies identify safer process chemistries that could be used for electronics manufacturing. So 18 products at this time from 6 manufacturers in that product category, and other standards have a different number of certified products. They've been released at different times, so they're each on their separate journey. Next slide, please. And this is my last slide, just to demonstrate how the green screen criteria and systems have been used. This is just 2 examples from the electronics world. HP has used the system to assess many different chemistries, including the alternative flame retardants that could be used in the products that they sell, along with the plasticizers that are used in the plastics and the plastic materials for their products. And Apple has used the system as well to replace the benchmark 1 and 2 cleaners and degreasers. It specifically used it to identify safer alternatives for those product category chemistries. So again, the system is used by industry, government, is referenced externally by NGOs as well, who want to get a sense of what is hazardous and how to define safer alternatives. And I think that's my last slide, and I'll hand it back over to Ali.
Thanks, Chris. That was fantastic and definitely gave us a great perspective on how the green screen and hazard data can be used to really inform safer substitution. And just before we jump to Krishna, one question, there's a couple questions. Ian, I know I see yours. I'm going to hold to the end because I think they'll be great for the panel as a whole. But one quick question for you, Chris, is how, from Braxton Lewis, how does the condition of use factor into the use of green screen tools? Oh, you're on mute.
Yeah. So how does the condition of use? And I take that to mean that the condition of use, I take that, so, I mean, I understand the question. So it's building in the exposure assessment scenarios, or the exposure scenario from the use of the product itself is how I take that question, right? So that is basically inherently not a part of the hazard identification side of the green screen system. And that is an intentional design choice based on what we believe is the best approach to identify hazardous chemistries and define safer alternatives. So the use case for the product is left out of the hazard assessment, hazard identification, because we know ultimately at some point in the supply chain, there is going to be exposure to either workers or the environment as part of either end of use or disposal of the product and materials. So we've taken the exposure scenarios and kind of the product use scenarios out of the equation for the most part. There are a few cases where we do acknowledge it, such as titanium dioxide in emulsions or solutions. So we do acknowledge it in very rare cases, but for the most part, it's not a part of our principles here at CPA and Green Screen. And I'm happy to go into other details or have a discussion during the discussion portion.
Thank you, Chris. Appreciate that. And just, I'm sure everyone can see in the chat, Mike and Sheila have been putting great links in to references that speakers have been making. So grab those if you want more clarification of those references. So I'm excited to introduce our final speaker, who brings a very powerful scientific and technical lens to this discussion. Please welcome Dr. Krishna Rajan from the University of Buffalo. And Krishna's work in material informatics is really helping discover new pathways to overcoming barriers to identifying safer materials, with the emphasis on avoiding regrettable substances. So Krishna, I'll hand it over to you.
Well, thank you, Ellie. First of all, I want to thank everyone for inviting me, and I really appreciate getting a chance to speak with all of you. So can we get the first slide up? Okay, this is the title. I'm talking about safer solutions for batteries, and I'm going to use the phrase materials informatics. Can I get to the next slide, please? So my talk really is complementary to what both Helen and Chris have said. So at one level, everything they've laid out very nicely has defined the challenges. They've shown how things are being done, the kind of the tools that are available to do this. And I at a macro level, if there's kind of one takeaway message I'd like to give to everyone, as far right at the beginning, is I'm trying to look at that same problem, but at a more granular level. And my argument is that granular level can enhance and strengthen all the things that industry can use and consumers can use, and at the same time open some new doors for finding alternatives. So the basic message of this, which is the science platform of the core project that I work with Ali, is how do we screen and select for safer materials, but do it with two things happening. One is how do you accelerate it from years to months down to even a few weeks. And two, how do we make sure that in the speed of making those decisions, that you can do it in a trustworthy manner? And that's a very, very challenging, difficult problem at so many levels. And so the work that we're actually doing, and I'm going to give a couple of slides, not to get too technical, but just to give a summary of what the logic of our work is, and then give you some examples of just part of this. The idea here is if we want to find alternatives, we want to not only avoid things that we know are hazardous, and both Chris and Helen have talked about identifying that is a very difficult and challenging issue, and they've got wonderful methods they've developed over the years, but we're also trying to understand why they are hazardous as much as why they work. So we're looking at this problem of screening in two sides of the same coin. One is we have a material, PFAS, solvents, whatever, where it is being used because very pragmatically it works for whatever application. But in the process of finding a substitute, we have to go beyond just saying find a material that doesn't contain it, but to finding the material that can maintain or if not improve the functionality. And this is not just an academic question, because if the issue is how is all these issues going to be adopted by industry, they need to have an alternative. It's very difficult to convince people to change, even if they want to, if they don't know where to go next. The second issue that I want to embed here, and I'm speaking as a material scientist, that materials are not, we define materials by their name, their chemical formula, but the behavior of a material in an area as complex as environmental health, toxicology, is due to a whole set of issues that go beyond what the label of chemistry tells you. And it involves how they're made, the way you process it, and how they change. And finally, and the other issue is how do we then find techniques and tools that these complex relationships can be used by everyone who is, whether they're in the research or in the user side. Can I have the next slide, please? So this is the goal of how we're approaching the problem, that we are trying to do two things at the same time, two things which are very conflicting. We want to design materials or chemicals, and I'm going to interchange the word materials and chemistry interchangeably, and I'll elaborate that in a second. But we want to deal with both the environmental health issue hazards and at the same time keep in mind why we're using them. And if you take a battery, and let's talk about a battery, it is an unbelievable, in fact, Helen, you raised this very nicely, it's a unbelievable materials landscape, not just in terms of chemistry, but that same chemistry sits in polymers, it sits as organic chemicals, it sits inside inorganic solids, and that same chemistry has very different functionality in different parts of the battery. And just studying each part alone, which we do in our program, is a huge challenge. And the other issue, and this is the paradox, is that at one level, we like to think that we have lots of data around us, but in reality, that data is dense in some areas, and most for practical purposes, it's sparse, and it's very diverse and challenging to combine. So the intersection I'm looking at here in terms as of a materials point of view is not just I put chemicals / materials chemistry, how and they're made, and the environment in which they're used. Can I have the next slide? So just to and this is the issue of where does the AI problem come in? One is, of course, is that the information is sparse. We have this dichotomy where we perceive when we hear of AI in our kind of social vernacular that we have lots and lots of information. We have lots of information. A lot of it is noise, and a lot of it is only in certain genres in their applications. But so when it comes to scientific and engineering problems, it's a very different scenario. Our actual reliable data that we have is small. The amount of data we need for certain things is difficult to get. And we have to solve these problems with a great deal of urgency. And this is a big issue here. And the traditional approach we still live off of to a large extent is we build on our experience and what we know, and we do experiments, we do models, we do tests, and you piece that information together over a long period of time. So our aim is to find ways to compress that as much as possible and very, very quickly. And I have the next slide. So this is my scientific slide. I'm going to just try to explain the logic. And this graphic is not my graphic per se, but there are graphics like this everywhere. But the message is the following. The cartoon on the left is to say I have a molecule. I have a chemical formula, and the graphic is just to show how they may be arranged. But the list there is just an example for this thing. But the idea is if I describe a molecule, a PFAS, a solvent, it has multiple characteristics. And those multiple characteristics are not just simply in the formula. To get each one of those characteristics sometimes cannot be measured experimentally, or it has to be done theoretically. And just to do each one alone is a massive amount of information that needs to be done by different methods, different techniques. And in the field of computational chemistry, for example, people specialize in each one of these in a very separate way. So that's one issue. And so then the second issue is we want at the right-hand side, and you take the molecule, and let's say we talk about toxicity and what Chris was talking about endpoints. The idea is you have an endpoint, hazard endpoint that you measure, you can see the environmental or health impact. But underneath that, there are issues that come back to the chemistry at a level that is not easily seen that actually makes that happen. And so what we are trying to do is to take the information on the left-hand side of this figure, put it through this magic box, which I'll figuratively call machine learning, and embed that into the structure, and we understand a mechanism as to what that means. In other words, we try to understand what actually contributes to that toxicity and what actually contributes to its functionality. So and discovering that fingerprint is the information that we spend our time trying to do. But to do that and to make interpretations, we have the challenge that we have to learn from the past. That has always been a historical issue. We can't change that. And so we like to, and that's where statistics come in. We say, if we know what has happened, can we predict or estimate what could happen next? And in a crude way, just doing a regression on a set of data points is really what that tries to do. But the problem is this. We have a lot more molecules in chemistry out there. And if you look at the chemical space of organic molecules, both that have been done experimentally and by computation, we're into the billions of information. And all that information data actually has evolved within the last decade. The second issue is on the inorganic side is a much slower rate, but we are now in a position where people have a knowledge base, nothing about all the issues, but just understanding how atoms and molecules are arranged in a given crystal structure for simple structures runs in the hundreds into the millions. But if you take a battery, we do not have, despite all the work we have, the amount of data we have on all the structural and issues on just the crystal structure aspects on the inorganic side of the battery and the organic sides of the battery is very, very sparse in terms of how much we need. So we have this imbalance. we have more information, but less knowledge about that data at the same time. And that's just rapidly diverging. So we have a scenario where this information imbalance is just growing at an exponential rate. And we have to somehow rein that in and to make decisions. Can I have the next slide, please? So I'm going to go through 2 or 3 examples. The graphics is not things that most of you will be familiar with to begin with, but I just want to explain to you, use this as a backdrop to explain the kind of questions we're trying to answer. So if I take the case of solvents, and in this case, what we're saying is we're asking the question on the left-hand side. There's a label there I call perovskites. Perovskite is just a term for a class of materials. Many of them are used in batteries, they're used in semiconductors, they're used in solar cells. But these formulas that you have on the left-hand side are just the kind of a generic name of these materials in terms of the complex chemistry. But the question we were asking is, why is a solvent used in making a battery? And if you actually do that, to figure that information out, you have to pile your way through tons of literature. It's not something that sits in a database. And so what this is where each line is information that we have traced from large amounts of public domain information about a given material used in the battery, how it's used at what are the different solvents that are used, that's the middle column. And then the question is, where in the process of making a battery is it used? Is it used in the process of mixing colloids? Is it used in the depositing the material? Is it used in the process of surface preparation? So if you take the actual steps in making a battery, material alone, forget the device assembly, it's very complex. And what this pathway, this plot shows is the threads of information we have about the use of given solvents in these different environments. Now, to make this plot, if I had to do it manually, would take months and months and years with lots of people. Now we have tools in what we call in the AI community, machine learning techniques, to read such papers, but to train the computer to read these papers such to extract that information is not something you go to ChatGPT and do. We have to construct models that can teach computers to understand battery chemistry, and that involves lots of manual labor. So this is the paradox I want to tell everybody up front. AI is not fast. To set it up in a useful way is a tremendous amount of manual labor and research, which is what people like us do to make these things viable. So here's a case where we're using AI to trace chemicals for material synthesis, but the reason I'm showing this is we can use this at any level. If you're talking about, we've done work, although I'm not presenting it here today, where we talk about the tracing of information on chemistry from geological and in fact geographical distributions. So if you have pollution at the measurements you're making in a river, where does that sit compared to the entire geographical and geological workflow on flow of information? This is the kind of things we can now do that we're not able to do before. Can I have the next slide? So taking that case of the solvents that we just talked about, that we identified, then we asked this next question of saying, can I understand where exactly is all this information, is a solvent being used under what conditions? So what we do is in this diagram on the left-hand side is figuratively looking at how we do our screening, if you wish. The screening involves, we define some metric that we're trying to screen at different levels. And in each level, we go from something that we can measure and see, and then go further and further down. Now, and you go from the blue to the orange to the gray to the green. The information, there's an intersection where we look at the amount of information we need to add and understand how the AI can figure out what needs to be done and check. And at every point, we need to check this to make sure what we have. And on the figure on the right, the complexity of that diagram is to deliberately show the complex relationships, how different chemicals are related to other chemicals in the making of one material. So the reason I want to show this slide is when we talk about a safer solvent, we have to understand that one solvent is not sitting by itself, is sitting with other materials, and is sitting in an environment of a complex array of processes. All of that information has to be captured, and that's one of the things we're doing in this whole issue of hazard assessment. So we're not looking at chemicals in isolation that you would have in a laboratory test tube, but how would they actually behave in an actual practical engineering and manufacturing environment. Can I have the next slide? And this example I'm going to show you in the other direction is, and this is kind of gives you an example of what we can do as an end product. We're looking here at, can we define, if we have solvents that are being used in a given industrial process, for in this case making materials that are in turns are used in batteries, we then are able to say we can extricate data from public domain information. As that domain information, I should say, doesn't only come from reading papers, but from large amounts of calculations that we use and do and ourselves. And we then are able to identify which solvents are used where and why they're being used. So if you're looking for a substitution, we should also be looking not just to find what can be substituted for that step, but we've also got to give people guidance as to maybe avoid that step altogether and change your processing so that that chemical is not used at all. So the point we're approaching is to use this chemical substitution in a holistic sense to make sure things work. And we're actually able to come up with, in a very challenging way, but it's difficult to do, but we were able to do it, where we can now give a prediction of saying, a binary choice. Is this safe? Is this unsafe? But we can also induce the level and quantify the level of uncertainty that you would have to make a decision. And that's where we are able to keep the trustworthiness aspect inside all the time. So behind all this calculations is the ability to understand how we can, in fact, use these things for different things. So, I use the perovskite example because it's used not just in solar cells, but it's used everywhere in batteries is one of the big examples. Can I have the next slide, please? Another one I'm talking about is PFAS, and one of the issues with PFAS, I'm sure all of you understand, is that it's not just one molecule, but it's a family of molecules, and these are used, and they're popping up and generated very rapidly in lots of ways. And one of the challenges with PFAS is that you can it has a basic formula, if you wish, but it's a very complicated molecule where one slight change, people will say it belongs to a different family. So if you can imagine PFAS being a massive tree with tons of not just leaves, but branches and sub-branches, that's what you have. So if you're trying to find ways to find alternatives to PFAS, how do you go through this massive complex array of information and kind of organize it and say, how do I know and why something is safe or not safe? In fact, the debate of what defines a PFAS has been around for a long time. And one of the things we got into is that we can't deal with the substitution problem if we don't find a better way to deal with this classification problem. And so, on one level, that classification has existed in EPA and other methods, but they've always had them in tables. But the tables don't give you information on how they're related, both in terms of multiple sets of properties. So what we've done is we brought these tools of AI, and you see a figure there that looks like a tree of networks of information, and what each dot there represents different types of PFAS, and the connecting are those which are defining how which families sit where and what their cousins are and what their sisters are and all the rest of it. And the reason we call this a map or an atlas, and the reason we do this is because now we can actually go into an environment, a chemical environment, and begin to understand what we substitute and where, and what the chances are of finding alternatives or safer alternatives, and for different applications. So we call it an atlas. It's interesting, although the EPA did not support our work, they have adopted these methods as part of their regulatory policy tools, and now other groups are using this. Now we've moved way beyond this, but one of the things we're using this for is actually starting to select and identify molecules that people haven't used and go into PFAS-free environments. So this is a very big issue. And the other part of this, with this kind of backdrop, we're now in a position, while doing toxicity of environment tests and all these others are slow and arduous to get accurate data, but now we can make predictions which can then target what the likelihood of a certain level of toxicity might be, and this helps accelerate where the experiments should be done, because you cannot test thousands and thousands and thousands of molecules all the time. This allows us to accelerate and offer to the toxicity community or the toxicology community ways to target their efforts to make fast decisions. And the next slide. So just to put this all in kind of as we try to conclude, that the way we are approaching this is, yes, we want to make and avoid regrettable substitutes. That phrase "benign by design" is one. But we're also, as a material scientist, I'm also trying to design materials so they work. So I'm trying to design with a given intent. But the issue that I want to raise here is that all the metrics we put into our analysis isn't just the molecule or the name of the chemistry. We're doing it taking into account its performance, its sustainability issues, how you make it, the way you manufacture it, and it's a continuous loop. And that continuous loop is what we do and why we use our techniques that we have. So just to end, and just my kind of summary slide is just to say what are the things we're highlighting in terms of our work in the core. Can I have the next slide, please? Is to accelerate and screening to guide targeted testing. We're discovering pathways for selecting chemicals and materials, not just chemicals and materials that exist, but we are now on the verge of actually identifying or creating proposals for molecules and chemistries that have never been made. And that's a very exciting issue, but that needs to be, that opens the door in this whole field. And on most importantly, it's not just a scientific academic issue, we have to understand why we're selecting alternatives as much as getting a solution. And and the fact that we are having an impact on regulatory policy issues, I think is a first step to show that these kinds of things are being seen valuable to the larger community. So with that, I'd like to end. Thank you.
Thank you, Krishna. That was fantastic. And it really gave insight on how we leverage informatics and data-driven tools to really overcome some of these systemic barriers. There is one very technical question. Braxton, I don't know if you want to actually ask it. I can read it too, but you might want to give a little bit of context on it, if that's possible to do it with our webinar technology here.
Sure, if I'm unmuted here. I'm curious if you're going so far down in your molecular modeling and characterization to look at individual like cellular reactions and protein folds or misfolds, which are now being associated to negative health outcomes or endpoints.
That's a very good question. The work we're doing so far in terms of how it interacts with the environment had been focused and not on the biological side, but on the inorganic side. So how does this stick to surfaces and other sorts of synthetic materials? But can we do this in terms of biological? The answer is yes, we can, and that's something we want to do. So that's my short answer to your question, and its impact on the dynamics of biological phenomena, 14 folding, and all these issues is very much something in our camp. But right now, our work with respect to things like PFAS have been on how it interacts with synthetic and inorganic surfaces.
All right, well, I appreciate it. It gives us more to work on as we go into the future.
Yes.
Thank you.
Braxton, while you're on, and Chris and Helen, if you want to put on your videos, that'd be great too. Do you want to just ask the green screen question too?
Oh, yes, volume. I'm looking at a total volume of compounds being used, and I'm curious if green screen is including that within its outputs as far not just identifying the molecule, but looking at total volume within a product or a process.
So amount of hazardous chemical or amount of chemistries in a certain process, right?
Yes.
Okay, so so green screen doesn't do that directly, but what we have is the chemical footprint project, which has metrics at the organizational level, so not process level, but it's like the next tier from green screen, right? So we have at green screen we have the chemical level, and we have the product level with green screen certified. The chemical footprint is organizational level, so they'll take a look at either brand or organization chemical footprint for specific chemistries, either benchmark 1, 2, or the specific criteria that they track. So, and in fact, that could be tailored to processes and manufacturing facilities, for example. So, so yes, that type of a metric is applied in a different system within one of the other green screen tools.
I really appreciate that. Thank you.
Thanks, Braxton. So I know, Helen, you started to answer Ian's question, but I just wanted to offer Ian to, if you want to pose that question to the rest of the panelists, or maybe some of that question was answered through what Chris presented. Then you can take yourself off mute and ask it. We might have lost Ian, but I think his question is still a really good one. I want to just add some context to it. So I think, Helen, you really stressed the issue of cost, driving all the factors. And if we can't really reduce the costs, how do we make these arguments to do safer substitution? And so this is really a question for everyone, because in this audience that we work with investors, we work with nonprofit leaders, governments, many stakeholders that have different lever points. And can you provide some insight, all three of you, on lever points that you think help really bring down some of those costs or justify the investment in the safer substitution? And what are some of those most effective levers from your perspective?
Actually, I do want to, since you mentioned cost specifically. So one of the things that we often talked about for the raw substitutions was a level playing field. So one of the benefits of having a restriction or like a law that's banning something, banning a substance, is that then everybody's kind of in the same position competitively. And if the generally accepted alternative is a higher cost than the original substitute, or a substance, but if everybody is paying the same amount, that is also potentially one way to get a change to happen. So having a lower cost is always a good, makes it easier to make that transition. But if you can't have a lower cost material, and usually new materials often are more expensive, then at least having a level playing field, going through a regulatory body to make that uniformly apply to a whole class of product or industry or whatever, tends to be helpful.
Thank you, Helen. Krishna and Chris, any insight from your perspective on that? Major drivers help reduce cost.
I think the issue of cost is always there, and I think, but how you measure cost is tricky, because there's the immediate cost of acquiring and of investing, but then there's the longer term costs of making changes or correcting mistakes. And I think this is and so that's one of the things that our tools can do, is that you can overlay onto it all kinds of information, from very foundational chemistry information to engineering type information on the processing and methods, and put in economic and other sorts of information. So what we're trying to do is to have a platform. We could, in principle, make it very, it can absorb a lot of information of different kinds. So people who may have different objectives and interests, we can help them make decisions.
And I think for me, I think the market itself is a huge driver in these cases, right? So as hazardous chemicals become highlighted in specific consumer products, and I think the first wave was cosmetics that had started 20 plus years ago, where hazardous chemicals were identified as an issue, and it was really brought to the forefront. And a lot of work stemmed from that initial conversation that spread to other materials, other consumer products. So I think between the retailer's attention to respond to that, to drive their supply chains, and individual brands being innovative to make the initial safer material selection, I think those are powerful levers to really drive toxicity reduction.
Thank you. Thank you for that. John has a question in the chat for Krishna. John, do you want to take yourself off of mute?
Yes. Interesting presentation, Krishna. I guess my specific question was on the PFAS front. Do you have any specific examples of how you've used your approach to identify alternatives, for PFAS in use in batteries?
Well, some of it is ongoing, but what we're doing now, for example, is if we know what the functionality of a certain PFAS is being used right now, can we find other molecules that might be have the same features? And that's the kind of things we're doing. That requires us to embed massive amounts of information in a larger chemical space to compare. So what we have done to make that happen is we're just in the process of getting this published, is to get a very comprehensive fingerprint of every PFAS that's right now in the EPA database, and that allows us to compare all the PFASs together in a common platform and a common scientific way, and that way we can use that as a screening tool to look for those same signatures in non-PFAS compounds. So that is kind of a quick estimation thing about how the logic of our work can help do that.
Thanks, Krishna. So one, sort of forward-looking question for all of you to think about is, what are some of the biggest breakthroughs, whether sort of scientific or regulatory or technology oriented, that you see could really transform, this field? And Krishna, I think you're in some ways speaking to that through material informatics, getting data in a way organized to inform a more benign by design approach. But we know that the change that we're promoting is going to take time. Do you see exciting things on the horizon that might help accelerate this transition, or you would like to see these things could happen?
I think they can happen. I think the work we've been doing with you for the last few years, I think, has put us in that position. I think where I see some exciting things going, but they have to be done cautiously, is finding, and that's what we're doing right now, is finding alternatives, but also in a matter of in a compressed time by a factor of 5 to 10 if need be. And I think, when Helen, you talked about having to make a decision in a few months, that kind of volume of information to digest is very, very hard. And I think the tools we're having can help make that process go faster. And the other one, which this is how it drives a lot of my work on the PFAS side, at least, is the same approach that we see in the drug discovery area. The drug discovery problem is the opposite to the toxicity problem. That same molecule that does good can be, if it does harm, it's obviously we want to avoid. And how do you find substitutes? So a lot of our work that I'm doing now in this area is derived from work I've done in the past in the drug discovery space. And I think there's I'm going to be optimistic about what we can do here as it is in other fields.
Helen, if you could wave your magic wand on what you see, given you've been in sort of electronics technology to battery startups to now AI.
I think that there's a race on for solid electrolyte, and I think electrolytes can be very problematic, and some of the constituents of electrolytes can be problematic, and the evolution of HF, in electrolytes over the life of the battery can be problematic. So I'd say that changes in the electrolyte world are probably the most interesting from a hazard perspective. I think there is some movement to move from NPE to aqueous formulations. So those are some things that are interesting. I think that there's just so much happening in battery chemistry, and there just will be for some time. We're going to start to see just lots of interesting new technical solutions come out. The big question is, are any of them going to be commercially viable? Even if they're technically viable, it's not clear, as the China battery industry has really solidified. Even though they are looking for innovation, it's sort of innovation for cost savings. They are innovating, but this is not really the direction of a lot of that innovation is not safer chemistry. And so as safer chemistry becomes available that, again, technically works, it's not clear what's the trajectory to get that into volume batteries. So I think that there's going to be really good technical work, and how much of it gets used, I'm not as sure.
Yeah, that's very insightful, and also, some promising changes, and great to hear about transitioning from NMP. That's been one of the more egregious chemicals to impact communities and workers. So that's certainly hopeful. Chris, I'm just drawing on Helen's lessons learned, and you now have been collaborating with some groups in China on the green screen, and given sort of Helen's sort of perspective on, like, you have to engage them or they have to be part of this solution, do you see sort of more traction on tools like the green screen in China as you develop relationships there and do education on the green screen?
Yeah, I think there's absolute interest in China in these types of tools, especially green screen. And so this year was actually the second year that I had gone to China and presented on a chemical regulation at a conference there. And overall, as I mentioned, there's really a ton of interest in understanding, okay, what are these systems? How are these tools used? How can they be implemented, strategically for their nation, in fact, on the regulatory side. So yeah, I think knowing that China is such a strategic organization for so many of product supply chains, including batteries, I think it's really helpful to know that they have absolute, genuine interest in hazard avoidance and green screen, and kind of building systems that can help support the goals that they also have in place for sustainability and chemical safety. So I think it's been really helpful to build those relationships, and we can see that they are going to be very impactful as time moves forward here.
I'm really glad to hear that that you're doing that engagement and you're getting that warm reception. That's really, really important. The great part about working with China is that once a decision is made to do a thing, they commit, 100% commit. So, getting that adopted, it could be a very fast change, or getting something restricted. There's a very fast timeline for getting things restricted once a decision's made. So that's really great to hear.
Yeah, and I can appreciate the point you just made around kind of their action and their commitment, and how they can just make things happen in a certain pace that is very different than the Western world. So yes, we're looking forward to the future with China.
Great.
Stephen, I see you have a great question in the chat. Can you take yourself off mute and ask it?
Yes, been active in the sustainability area for a while with Boston Common Asset Management. And we're wondering on the battery area, Helen, you talked about how battery manufacturers are really just looking at cost, but if there is something that reduces their cost and is also more sustainable, then they'll go for it. But what should investors ask of big battery manufacturers, or what should we first ask of them if there's a first start things we should ask to encourage them to use safer chemicals in their battery manufacturing and in their products?
Well, I'm going to do a plug for the chemical footprint. There's work going on right now to extend the chemical footprint project into the battery space, and I think that that's a very good way to go, is to just bring that discipline. We're not like today, it's not quite ready today, I guess, but the idea of holding them accountable for the decisions that they're making in their chemical choices, in their administrative controls, in their waste management, all of those things are really important to start holding, not that they're not held accountable, but more accountable to a higher standard, I think is going to be very important. And, to Chris's point, I do think that there's a certain openness to it. It's just that there's not as much pressure on that as there are on cost, because cost is just it's an existential crisis for them right now. And so it's very tough to be concerned about something that's not immediately existential when you've got that kind of cost sort of Damocles kind of hanging over you. But, start to bring that additional requirement or expectation, I think with the overall view of their chemical usage will be really, really good for the industry.
Thank you.
Thank you, Stephen, for that question. And Stephen and Helen and Krishna have all been a part of a review process, and Sheila Davis on a chemical footprint battery survey. So the chemical footprint project is a part of Clean Production Action, and it creates a whole framework to measure your use of chemicals of concern and start to methodically reduce them and transition to safer alternatives. And HP has been a big leader in that space, along with retailers like Walmart and Target, and investors have been pushing for companies to engage in that. This is only the second time we're going to actually tailor it for a specific sector. And we hope that that will be pushed out in January. We're really excited about that. I know we are coming at time. I would just want to allow just a lightning round across our panelists. Any last quick either call to action or final thoughts you want to share with this group before we come to a close today? I can start with Chris and then go Krishna, Helen.
I think for me, it's the fact that the battery space is a prime kind of product category or area to be working in for a lot of the reasons that have been pointed out on this call, right? So it's got kind of the perfect storm of, engagement with China, ability to identify hazardous chemicals using, the tools that are out there in the system. And I think there are certainly stakeholders that can be engaged to carry this work forward and to really demonstrate leadership and progress in these areas, right? So we've already seen that for a lot of electronics companies for hazard reduction, and I think they can be scaled, directly to batteries. So yeah, more of just looking forward to a lot of progress in the future.
Krishna.
Just to build on that, I think the thing about the battery space is it has, as I said, a massive amount of materials landscape covering different chemistries, different genres of materials. But to solve the problem with respect to batteries, they have to be looked collectively. And right now, when we work in batteries in individual parts, on the electrolyte part, on the solvent part, on this. And I think the part that what I presented today is the argument I'm making is we can integrate that information. And because at the end of the day, it's the battery as a whole that we want to make safer and reliable, and what the kind of things we're talking about, I think, is an opening for that to happen.
Krishna and Helen.
I just want to say that I think the time is right just to kind of rebalance a little bit of how people think about the sustainability of batteries. My observation is in the last 8 to 10 years, the focus has really been on the decarbonization aspect of batteries, and that was really the primary KPI within the sustainability space. I always felt like carbon sucked the air out of the room when we tried to talk about these other topics. And so, but I don't want to decarbonize and leave a toxic legacy. So I think it's really important for us to not just use batteries to make this clean and make this transition to electrification, but that we also have to keep the focus or balance that with this view of chemical hazard, because there are some very, very long-term implications and impacts that can come from all of the waste that's going to come from batteries at end of life, that if we don't get ahead of, it's going to be a very not sustainable, the opposite of sustainability in terms of the end result. And so we'll be decarbonized with this very toxic impact. So now is a really great time to start balancing that message, so that it's not just global warming, it's also the toxicity reduction as well.
That's a perfect note to close on. And I just want to thank everyone for spending the 90 minutes with us. This is a series. We will continue in 2026. We are building a network. And so just first, if you want more information on any of the organizations co-sponsoring this, you see QR codes. Please reach out to us if you're interested in joining our network, even initially through a listserv, to stay engaged. We really need all of you to drive this change forward. As you can tell, there are exciting opportunities and big barriers, and we're really trying to grow a community of change agents and leaders. And so thank you again for joining us, and a big shout out and thank you to our amazing panelists for all the insights you shared today.
Thank you. Thanks.